inside the doctoral school in civil engineering and architecture here at the University of Cagliari, and it's shared by myself and my professor Fernando Fraternali from the University of Salerno. So the topic of Professor Fraternali is here on my side.
Hi, everyone.
And he will share the responsibility of giving classes in this class. Now, thank you. So the topic which will be addressed is this about mechanical behavior of elastic, curved, and twisted beam using a geometrically exact approach. That means that we are dealing with curved members like those shown in this picture. For these members, it's possible to find some closed form solutions, so not only finite element simulations, and it's a good idea to provide you with a method for using these machinery in order to be able to compute, evaluate stresses and displacement in some, at least simple cases. We will be mostly concerned with linear elastic behavior, so we'll not go to speak about large strain, large displacement analysis, but only within the framework of small displacement and infinitesimal strain. However, what is not restricted is the shape of the axis of the beam, so we will be able to deal with curved, twisted beams, and also with a strong beam exhibiting a stronger curvature. So you will see also that for such kind of problems, standard extension of the invariant theory cannot be applied, and more refined models are necessary. So the schedule of the classes and the tentative program is given here. So we are starting after many attempts in the past. Today we are finally starting the class. It was a long awaited course, this one, because we were planning to give it a couple of years ago, but then there was COVID, and then in last January we were planning, but there were problems for matching our schedules, and so finally we decided to fix the dates and now be tied to these dates. So we are starting today, and the class will continue tomorrow in the afternoon, on Wednesday both morning and afternoon, and finally we will conclude the class on next Thursday. So this is a tentative schedule of what will be taught, and this is the Italian thing. I would like to introduce you to what moved our interest to this topic, and it was this famous report that Professor Fraternali and his mentor, Professor Ascione, wrote several years ago in Salerno.
Yes.
You see from the typeset that it is a rather aged system, let's say. However, vintage. It's kind of vintage report. However, what was really interesting about this report, the first time I got it in my hands, was that it was self-contained, and it had an elegant way of introducing to these curved structures. And there was nothing similar in written in an organic way in the available literature. So somehow forced Fernando to prepare an English version of it, because still in the international literature there is a lack of reference text on this topic. And so we planned to do this, and we are on the way of performing the translation, also with the help of Mario Spagnolo, who is on my back and is trying to get a record of this class. And so this is the main idea that moved us to this topic. Yes.
So yeah, just to complement what Antonio said, I was a child when we wrote this report. Just kidding. This was basically I was a student, and Professor Schoen involved me in this work, which started as an educational report, writing an educational report for the students, and next it continued with the research activities. So my first research activities were on curved beams, indeed, and we extended the theory that we will go through in these days. We extended to laminated beams, to composite beams, and so this was the follow-up of this initial activity, which was had mainly an educational character and was addressed to students. So as Antonio said, there is a lack in the literature of a theory of a textbook or lecture notes that deal with curved beams and also curved structures, also shells, which are mathematically correct, mathematically exact, in the sense that we will explain during these days, but at the same time have an engineering approach. So most of the available textbooks have a mathematical flair, have a mathematical character, and so they deal with the abstract theory of curvilinear coordinates, and so there is a lack of simplicity for engineering students for these approaches. While on the other hand, there are no engineering approaches to this topic, to this subject, and so that's why this notes that we have significantly, with the help of Antonio and Mario, we have significant. We have not only translated into English, but they have collaborated to enrich the content, and it's a very rich. We have produced a very rich manuscript that will form a textbook in a future, in the near future. And so in this course, we are experimenting the use of this educational material for illustrating to you, because obviously it's much easier to illustrate directly through interaction with the students a topic while instead of reading a book on your own. So our goal is to illustrate these notes, to transfer to you our engineering but exact approach to the theory of curved beams. Thank you. I'm very happy of finally being able to be in Cagliari. I have chosen the hottest week of the year. It was my goal, and I succeeded. So luckily, I have to say that I'm enjoying Cagliari, and here in the end, the weather is even better than the weather in Salerno, which is more humid and more difficult to bear. So thank you, and Antonio will start today, and next I will continue tomorrow, and in the following days we will alternate, and so hopefully you are very welcome of asking questions and just asking any questions or on points maybe that are not clear to you. and we look forward to interacting with you and to transfer to you this work that we have prepared, hopefully in a successful way. So thank you again, and go ahead, Antonio.
Grazie. So this is a short list of a few books that were used for preparing these notes. And as you see, the topic is not a new one, but it is really hard to find a self-contained introduction to this topic. And so, for instance, in English, some important contributions are from the famous book by Love, a treatise on the mathematical theory of elasticity, which is almost 100 years old. Then there is this book by Oden and another one by Wempner about the mechanics of solids or of elastic structures. And some contributions are, of course, available in Italian. One is the book by Benvenuto, which was about the kind of development in the history of the strength of material. And also the book by Baldacci, the second of the two books, which has some chapters about curved bits. Reference is also made to this book by Ashon and Grimaldi about some elements of continuum. After telling this, we should continue with, okay. So, first of all, we will start recalling some important topic from differential geometry. So, the properties of curves in the space. So, fundamentally, we consider a curve in the space like this one. And we can describe this curve by giving its vector representation, telling that the position of any point of the curve can be described as a vector depending on one parameter, and this parameter can be chosen in several ways. The most convenient way is to choose the arc length. So the length, a curvilinear abscissa, which gives for any point the position of the curve in the space. Of course, this is a vector equation you can develop by components. So if we decide to call with an index 1, 2, or 3 the three coordinates, then this equation can be represented by three scalar equation, giving the coordinates as a function of the curvilinear abscissa of each point belonging to the curve. With this curve, we can describe a vector, a unit vector, which is at any point tangent to the curve itself. And we will denote this vector by the symbol. And since we have chosen the arc length as a parameter, then we are sure that this vector is always a unit vector. If we had chosen a different parameterization, as we will see next, then probably we would not get a unit vector, but we could always define a unit vector by dividing the vector we get by the derivative of the curve with respect to the parameter by dividing it by its magnitude. So, along with this E3 vector, we can find a triad, the so-called fundamental triad, which is consists of three mutually orthogonal vectors, which change direction from point to point, but that are at any single point of the curve three orthogonal. The second vector can be defined as a second derivative of the position vector of each point of the curve with reference to the curvilinear abscissa. But if we take only the second derivative, we would not get generally a unit vector. So we have to divide it by its magnitude in order to get a unit vector. This second vector is called the principal normal. And indeed, we can see that if we take a vector E3 and we take a derivative of it with respect to the arc length, it's exactly like taking the second derivative of the position vector of each point of the curve, and this gives a vector which whose magnitude is not constant, but who happens to be orthogonal to the previous one. Why? Because E3, as we have seen, is a unit vector. So if we take the dot product of a vector by itself, we get a constant value. So if we take the derivative of this dot product with reference to the arc length, and we develop it, it would be 2 times the derivative of the 3 with respect to S times multiplied dot product by E3. And so, since the derivative of the constant must be 0, so the dot product of E3 prime times E3 is 0. So that means that the two vectors must be orthogonal. The third vector of the triad is called E1, and it is defined in order to be to provide a right-handed triad. And so it can be defined easily as a cross product of I2 times I3. And so E1, E2, E3 are respectively the unit binormal, the unit principal normal, and the tangent vector to the curve. Of course, we can, two vectors can define a plane, and so by taking two vectors at a time, we can define 3 planes, which are represented in this figure. So the plane that contains E2 and E3 is called the osculator plane, and it's a plane that approximates the curve in the sense that locally the curve lies on this plane. Then there is another plane which is called the normal plane, and which is a plane defined by the binormal and by the principal normal. And this plane has the property of being at any point orthogonal to the curve. And finally, there is a rectifying plane, which is a plane defined by E1 and E3. And this is a plane which rectifies the curve in the sense that locally the curve belongs to this plane. Now we can see some important properties. The first plane we have introduced, the osculating plane, is a limiting position of the plane which is passing through the tangent to the curve at 2 points, whose position differs by a standard increment of the arc length, delta s, when this delta s tends to 0. So if we develop by Taylor's formula the difference, the position of vector x times s plus delta s, that is equal to x of s plus the derivative of x with reference to s multiplied by delta s plus the second differential of delta s times 2, multiplied by a second derivative, and plus a vector epsilon, which is infinitesimal with reference to delta S. So the vector, which is defined as x of s plus delta s minus x of s minus delta s dx over the s, is parallel to this vector, second derivative of x with reference to the s twice. And on the other hand, this vector is a linear combination of the position vectors at 2 points of the curve and of the tangent vector to the curve. So it is coplanar with them. So that means that the vector, which is written within round parentheses, is parallel to the plane, and in particular, this plane contains the second derivative of x in its limiting position when delta s tends to 0. So, if the considered curve is a plane 1, then the osculating plane to any point of the curve coincides in any point with the plane of the curve itself. A curve which is not plane is called a space curve or a skew curve. So the first concept that we can grasp from here is the concept of curvature of a space curve at a point x, which can be defined as a limit when the increment of the arc length delta s tends to 0 of the ratio between delta phi over delta s, where delta phi is the angle formed by the tangent lines to the curve at 2 different points, when, of course, the length of these increments tends to 0. So, if we denote the curvature by 1 over rho, then one has that the limit of this ratio is exactly the curvature. Now, it is possible to show that the sine of this angle can be computed as, in absolute values, as a magnitude of the product of vector E3 times E3 star, which is a vector, tangent vector relevant to the new position. And in this way, remembering that as delta s tends to 0, also delta phi tends to 0, and moreover, the limit of delta phi tending to 0 of the ratio between the sine of delta phi and delta phi is equal to 1, it follows that 1 over rho is exactly the limit of this vector product divided by delta s. And so, again, by using sorry, we are trying to...
Già stai condividendo, devi ritornare sullo schermo.
E dov'è? Aspetta. Ok. So, Taylor formula truncated of the first order term, and so we can expand E3 star as a function of E3 and of its derivative, and so we can write this expression, and again we can see that this is the resulting limit when delta s tends to 0. So 1 over rho is nothing but the magnitude of the derivative of Z3 over ds. And so it's the magnitude of the second derivative of the position vector with respect to the arc length. So we can see that E2 is then rho times the second derivative of the position with respect to the arc length, and so is rho times the derivative of the tangent vector with reference to S. This rho is called the radius of curvature, and it becomes larger and larger when the curve approaches a straight line. So for a straight line, the radius of curvature is infinite, and its reciprocal, which is curvature, tends to 0. This gives the idea of how the curve change its tangent in the osculating plane. Instead, we can be also interested in defining the behavior of the space curve in introducing the concept of torsion, which gives the idea of how far the curve deviates from the flat course. And so it is necessary to refer to the way the osculating plane changes, moving from one point of the curve to the other one. So again, we can define the ratio between the angle formed by two osculating planes to the curve at two different points. There should be a, no, there is not a figure about that, sorry. And so we can define in a similar way the concept of torsion, which is the ratio of 1 over tau, and represents the magnitude of the derivative of vector E1 with reference to S. So torsion is essentially a positive number and gives an idea of how far a space curve steps away from the osculating plane. It's reciprocal, which can be thought of as a kind of radius of torsion, becomes larger and larger when the curve sticks on its plane. It is possible, however, to associate a sign to the torsion, and the way of associating it can be done by this reasoning. So we start from the consideration that the dot product of the two vectors, the binormal and the tangent, must be 0. And so developing, taking the derivative of this dot product, we get that it is 0. And so remembering that the derivative of E3 with reference to the S is nothing but E2, we can write down this equation, and that shows that since E1 and E2, E1 and E2 are orthogonal to each other, then it is also 0, the dot product of the derivative of E1 with respect to the arc length times multiplied by E3. So this vector is orthogonal to E1 and also to E3, and so it is parallel to vector E2. So the convention is assigned to 1 over tau, the sign which belongs to it if the expression d1 over ds must be 1 over tau times E2. An important consequence of this moving triad is that we can get some relation between the derivative of the orthonormal triple, which constitutes the moving triadron, with respect to the arc length S. Two formulas have been already obtained, and these are exactly these, so that the derivative of E1 with respect to S is nothing but E2 divided by tau, and the other one is this one that tells us that the derivative of E1, E3 with respect to S is nothing but E2 times R. So the last equation we can produce is this one. So we take the derivative of E2 with respect to ds, so if we develop the derivative of the cross product, we get the derivative of E3 with reference to S times E1 plus E3 times the derivative of E1 over ds. On the other hand, we know already what is the derivative of E3 over S, which is E2 over R. And here we know that d1 over ds is exactly E2 over tau. So we take advantage of the cross product of E2 times E1, which makes minus I3. And so this term gives us minus 1 over rho I3. Instead, this one is 3 times E2 is nothing but minus E1 divided by tau. So finally, we get these three relations. So the derivative of E1 with respect to S is 1 over tau E2. The derivative of E2 with respect to S is minus 1 over tau E1 minus 1 over rho E3. And the derivative of E3 with respect to S is nothing but E2 divided by rho. So with this machinery, we could now switch to some examples just to maintain some applications. So, for instance, we can consider again a generic point which moves along a trajectory, which we can think this trajectory is nothing but a curve in the space. And so we can describe the position of this vector as the position vector of P with reference to the origin O. Then, if this position is described by a parameter alpha, whose coordinates are component of the vector, we can express again that the coordinate x, y, and z of the position are a function of the non-parameter alpha. Then the elementary vector dp, infinitesimal displacement, is going to connect points which are extremely near on the line. And so by taking the derivative of this with respect to the parameter, we can get a vector which is a tangent vector. Of course, in general, this is not a unit vector because its magnitude depends not only on P prime, but also on the alpha. But if we take a point on the curve P0 and we evaluate the distance along the curve, so we introduce a new parameter called S, then the differential of this S is exactly the magnitude of dp. And so, on the other hand, this dp is nothing but dp over d alpha times d alpha. And so, we can see that ds over d alpha is nothing but the magnitude of P prime. And on the other hand, we can call that the ratio of the S over the alpha is S prime of alpha. So, as a conclusion, we see that S prime as a function of alpha is equal to the magnitude of vector P prime as a function of alpha. And so integrating, we see that S is nothing but the magnitude of P prime integrated between the two extremes alpha 0 and alpha. So P prime is tangent to the line L, and in general, as a function of alpha, is not unit magnitude. But we can always define the tangent vector by taking the ratio between P prime and its magnitude. And so this vector T is effectively a unit vector. And so this suggests also a way of changing parametrization. So if we consider that P prime as a function of alpha divided by its magnitude is nothing but dp over the alpha times 1 over the magnitude, and on the other hand we have realized that the magnitude of dp over the alpha is nothing but S prime, we can write down formally this expression, and so we can recognize that is the derivative of P with respect to the arc length. So T, the tangent vector, is a unit vector if we consider the parametrization of P as a function of the arc length. Then, of course, if we consider that its magnitude is 1, we take the derivative here. Sorry, but these are all some old notes, and we are using a different notation for the dot product. Is intended with a cross here. And so that means that the derivative of T, the magnitude of T must be 0, and so T prime dot T must be equal to 0, and so T prime must be orthogonal to T. So, given T prime, the derivative of T, we can define a unit vector normal, which is given by the obtained by T prime divided by its magnitude, and this is again a unit vector. So if we call the T prime as 1 over R, 1 over R is the curvature, and R is the radius of curvature. So the radius of a circle which locally approximates the line. And so N is nothing but T prime divided by the curvature. And so we can write down this in this form. The third vector, B, can be the binormal, is a third element of an orthogonal triplet, which is a right-handed one. And so with a cross product, which is denoted by this wedge here, B is the cross product of T and of N. And of course, we can see that if we express T and N as they are done, we can see that the expression of B as a unit vector is exactly this one. Now let's check with an example if this machinery gives us some useful results. So let's consider a circle and the point moving along this circle. So the position P over alpha can be given this vector expression, so x of alpha times I plus y of alpha times j plus z of alpha times k, where I, j, and k are the fundamental vectors of the orthogonal system. Then we recognize that the position along this circle can be defined through the angle alpha and the radius of the circle, which is called A. So x of alpha is A cosine alpha, y of alpha is A sine of alpha, and z of alpha is 0. Then, if we take the derivative of P, we obtain the result. So we obtain minus A sinus alpha I plus A cosinus alpha j plus 0k multiplied by the alpha. And so we recognize that the derivative of x, y, and z, x prime, y prime, and z prime, are nothing but the derivative with respect of alpha of the components. So we can see that the elementary length of the position, the elementary length, arc length, is given by the magnitude of dp, so can be written as the square of x prime plus the square of y prime under the square root. So here we have sine alpha squared plus cosine alpha squared, which makes 1, multiplied by alpha squared under the square root, and so we get simply the alpha. So the arc length S is nothing but the integral of ds between a given value of alpha, let's say 0, and the current value alpha, and so the arc length is nothing but r, the radius a times alpha, which gives us the length of the arc. And we can see that this is reasonable because if we consider particular values of the angle, we can see that when the angle is pi over 2, the length of the arch is r, the radius a times pi over 2. For alpha equal to pi, the length of the arch is r times pi, and if we consider a complete circle angle, so 2 pi, then the length of the circle is exactly 2 pi times the radius a. So now we can change the parameterization and use instead of alpha s, but s is given by I times alpha. So alpha is nothing but s over a, and rewrite the equation by expressing it as a function of s. Then the components as a function of s are a cosine of s over a, and for y is a times sine s over a. So p prime is a under the square root of square of sine plus square of cosine, and this is exactly a, which t, the tangent vector, is the if we look at p prime defined as a derivative with reference to s, we get exactly minus a sine s over a times 1 over a plus a cosinus of s over a times 1 over a. And so we get exactly that t is minus sine of s over a I plus cosine s over a j. And so we see that its magnitude is exactly 1. In particular, we can check the direction of the tangent vector to the circle at different positions. So for instance, if we select as a position alpha equals 0, so s equals 0, so at this point, we see that for s equals 0, the tangent vector is given by this expression when we place alpha equals 0, and so it is simply given by cosine of 0, so j. For t evaluated at alpha equal pi over 2, we get that the tangent vector is directed in the opposite direction as the x-axis. For t in corresponding to alpha equal to pi, we get that it has the director along the opposite direction to the y-axis. And again, if we select as a position here, 3 pi over 2, here the tangent vector is directed exactly as the x-axis. Okay, so we can now compute its first derivative, so t prime, defined as the derivative of t with reference to the arc length. And so the derivative of t with reference to the arc length is given by this expression here. And so we get minus cosine of s over ai minus sine of s over aj times 1 over a. And so its magnitude, which can be computed by taking the dot product of t prime by itself, is 1 over a, and so is 1 over r. So the curvature is exactly given by the curvature of the circle A. So in the present case, curvature is 1 over a, and so the radius of curvature, so the radius of the circumference, which point by point is locally approximating the curve, is exactly equal to the radius of the curve. So n, the normal vector, is nothing but t prime over its magnitude, and so is given by this expression minus cosine of alpha e minus sine of alpha j. And so this is a unit vector, as we can see if we take its magnitude. And now we can check what is the orientation of the normal vector to the curve. So for instance, for alpha equals 0, we get exactly minus e. So in this point, the orientation of the normal is exactly opposite to the x-axis. And similarly, we can check that the position of the normal is exactly as expected. Finally, the binormal B can be defined as a cross product of t and n, and if we check it, we can find that it is directed at every point along the third vector normal to the plane, and so it is a unit vector naturally given by k. Another example is here, and in this case we can think of using as a curve not a circle but an ellipse. And so a parametric representation of the ellipse is this one. X is a cosine alpha, y b sine alpha, where a and b are the length of the semi-axis of the ellipse. Of course, if b is equal to a, we go back to the circular case. So if we compute the derivative of the position vector, we get this expression. From here, we can get the length of the arc length. And we see that the arc length has this complicated form, because now sinus, square of sinus and square of cosinus are not multiplied by the same amount, but by different quantities, a square and b square. And so if we compute the length of the curve from alpha equals 0 to alpha, we get this expression. If we extract if we use the identities as cosine square is 1 minus sine square, we can write it in this form, and then extracting b over a, we can write down the length of the curve of the arc of the ellipse in this form, integral of from 0 to alpha of b multiplied by the square root of 1 plus chi square square sinus of alpha integrated in the alpha, where k square is nothing but the difference between a square minus b square divided by b square. And so the length of the arch is now expressed by an elliptic integral. So this is now the tangent vector, the unit tangent vector. And again, we can check that the position of the tangent vector at different points of the curve is exactly directed as we are expecting. From t, we can take the derivative with respect to s and obtain so t prime. T prime results has this expression, and taking t prime and divided it by the magnitude, we get the normal vector. Once we have the normal vector, unit vector, we can detect, construct the third vector as a cross product of t and a. Final example, before going back to our definition, it's a sect of helicoidal curve. So the helicoidal curve is this, can be described in vector terms by giving its position in this form. So x and y are given by follow a circular path, so a cosinus alpha and a sinus alpha, but there is also incrementing the z coordinate, which can be given by p over 2 pi alpha. So every circle, so when alpha makes a complete turn, we move up by an amount given by p. So we can take the derivative of p, and so define dp as a function of alpha, and that gives us this expression minus a sinus alpha dA I plus a cosinus of alpha d alpha j plus p over 2 pi d alpha k. So we see that the element of arc length is nothing but the magnitude of dp, and so we can collect d alpha, and under the square root sign you get a square sinus square alpha plus a square cosinus square alpha plus p over 2 pi squared. And so we see that the alpha is outside the square root sign. Here we have this time the square of the sine of alpha and the square of cosine of alpha was multiplied by a squared, so that gives 1. plus p square over 4 pi square. And so we can see that ds is d alpha multiplied by the square root of a square plus p over 2 pi squared. So if we call k this square root, we can see that the length of the helicoidal arc from alpha equals 0 to generic value of alpha is nothing by k is a constant times the alpha. And so for s equal alpha equals 0, s is 0. For s equal 2 pi, we see that the value is 2 pi multiplied by k, so can be written as the square root of 2 pi a squared plus b squared. And this is exactly the length of the helical. We can think of rectifying it by extending on a cylinder. Once we know this, we can compute the tangent vector. The tangent vector is nothing but dp over dA divided by its magnitude. And so we see that gives us this result, minus a over k sine alpha I plus a over k cosine alpha j plus p over 2 pi k times the unit vector k. So we can see that, for instance, the tangent vector for alpha equals 0 is not lying in the plane, but is inclined, so has components both along j and along k, and so on. If we take now the derivative of t prime, we get, however, this result because the derivative with reference to alpha of the last term is 0. And so we get that t prime lies everywhere in a plane, in the plane containing I and j vectors. So t prime is given by this expression, and so the normal vector, unit normal vector, which is t prime over its magnitude, gives us a times divided by a squared plus p over 2 pi squared. And so we see that the normal vector is always orthogonal to the vector parallel to the k-axis. The curvature 1 over r is given by this term, so a over a squared plus p over 4 pi squared, and this is always smaller one than 1 over a, and so the radius of curvature is always greater than the radius of curvature of the circle. Finally, the binormal b is given by the cross product of t and n. If we make the cross product, we can find that x expression is this one, and so there is also a component along the k-axis. So we see that n is always lying in the plane, but t is not orthogonal to the z-axis, and so b has components also perpendicular to k. On the other hand, from this expression, it's easy to see that the magnitude of b is equal to 1. Okay, so now we should go back to what we have learned so far and try to apply it to the...
I think we can give a little break.
We want to find... Okay. Let's take a break.
I will do that, but
okay.
It's your choice. It's your
no,
choice.
No, okay, it's good. Let's have a
we
break.
are switching topics.
10 minutes.
10 minutes.
10 minutes. If there are any question, please let us know and we can try to answer.